Okay, we're going to continue the lecture we started last time. We were talking about the estimating the difference of two population means or two population proportion. Uh, and today we're going to be talking about the testing the same. Uh, when you're testing the difference between two population means or two population proportion, you're testing whether those means are different, whether those proportions are different. When would you use that? For example, we have election coming this year, presidential elections, so you might be interested in the difference of the proportion of the women that will vote for a Democratic candidate and the proportion of men that will vote for Democratic candidates. So that would be the difference that you might be interested in. Or you have a situation that you have workers working in one company and working in another company doing the same job, and you might be interested in whether they have different wages. Those are the kind of the things you might be interested in. There are plenty of other examples when you are using the tests for to find out whether there is a difference between the means of the two populations. Okay. Now we do have here z-test and t-test, and for the proportion we have only z-test. So how is that going to look like? Well, for the null assumption, in every case we're going to use the assumption that the means or the proportions are the same. So the mean of the population X is the same as the mean of the population Y. And then the alternative hypothesis would be that you would say that the mean is different. The mean of population, the means are different. The mean of first population is not the same as the mean of the second population. You can be more specific about it. You can say that the first population, if you have evidence of that, has higher mean than the second population. Or lower. This would be the right tail test. The left tail test would be lower. There's almost never a need for a left tail test. You could just simply elect to have your sample that has bigger numbers in it to be your first sample, the X sample. In which case you will always be doing either this test, the test that the mean of the first population is bigger, or you're going to be doing this test, which will be two-tail test, which means that the means are just simply different. But then again, of course, you could use a left-tail test. It's up to you. When you're doing the left-tail test, of course, you're going to have the test values are going to come up negative, so you have to have critical values that are negative, so you have to be careful with that. The test value will be based on the central limit theorem. Every z-test is based on the central limit theorem, just like a z-estimate. So you have to have a central limit theorem, which will say that when you make the difference of these two guys, which is the difference of two sample means, this would, when you subtract the mean of this, which would be the mean of this guy minus the mean of this guy, which are the population means. That's what the central limit theorem says. And when you divide that with the standard deviation of this thing here, and we argued last time the standard deviation of this thing here would be the radical of the variance of this guy plus the variance of this guy. The variation add up. And the variance of X by the central limit theorem is going to be this guy. This is the sample size of what you have in the sample X. And the variance of this guy. And then again, N2 would be the sample size for the sample where you have the Y items. Okay? So this is supposed to be, central limit theorem says, it's supposed to be, if this is true, Z value. If this is true, then this is also 0, right? Mean of X is equal to the mean of Y, then this is 0. Now, if this is so, then we can just simply erase it. Which makes the formula a little bit nicer. So now I can squeeze this a little bit. I'm going to put it a little nicer here, so I don't have to have this much of a fraction. I'm just copying that what I had moments ago. And then, of course, I have rejection criterion. Rejection criterion is that this guy would happen to be in the tail, or in the tails, one of the tails. In here, or in the right tail here, or in the left tail here. I will never use a left tail test, so again, left tail test could be used, but that's only if you're, having the sample Y to have bigger values than a sample X. You can always have the sample with bigger values to be your X sample, right? And that way you can avoid the left tail test. And so this is going to be based on the bell curve, in which you're going to have tails or right tail with some particular significance that you want. Okay, so let me give you an example. Example is number 4 from the text, the lecture, which is on the blackboard. In that example says, Professor Flint has 2 groups of students, the morning students and the afternoon students, in the same class. Let's call it statistic class. Okay? In the morning group, he has 30 students. In the afternoon group, he has 33 students. In the morning group, on the final exam, he had a score, an average score in the class 71.2. Not everybody's scoring C, so there will be variation there, and the standard deviation is 9.8. In the afternoon group of 33 students, he had a final exam, and in that final exam, the score worse. They got a D plus 65.7. They also not everybody gets the same grade, so the standard deviation is exactly the grade difference, 10 points. So this is his story. The question is, are the morning students better? Because in this class, obviously the class he has, the morning students are better than the afternoon students. But the question is, he's asking himself this question: are the morning students generally better than the afternoon students in this particular type of a class, statistics? That's his question. Does he have enough evidence to conclude that the morning students are better than the afternoon students? So, okay. So here is my story. The morning students and the afternoon students score in the population, all of the possible students you can have in the morning and the afternoon, score the same. Okay, we do have an evidence that that might not be the case, and the evidence says that morning students are better. Morning students' mean is higher than the afternoon students' mean. Okay? So the only thing we need to do is to calculate the test value. So the test value is going to be 71.2 x bar minus y bar. And again, notice I choose the x to be bigger, with bigger numbers so the students to score better, right? And down there I need to have these numbers. Well, I do have 30 students in the first group, I have 33 students in the second group, but I don't have a population standard deviation, I have the sample standard deviation, S. Well, we know that in case of a large sample, when we are doing a z-test, if you have a large sample, you could use the sample standard deviation instead of population standard deviation. Now, if you have a population standard deviation, just plug them in. I just have a sample. But I have a large class, 30 students, large sample, 33 students, large sample. Okay? So, this is, you must be aware of that, an approximation. An approximation, I replace the sample standard deviation with, population standard deviation with the sample standard deviation. I'm allowed to do that if I have large sample. This ought to be calculated, but I have 2.203. I'm going to leave that to you to verify. And now the question is, do we have rejection? Rejection criterion. We're going to use a 5% significance. When you have nothing better, that's a customary one. So right tail, we know that that value must be 1.645, Z value, Z critical value for the right tail of 5%, right? That's something to remember. If you don't remember that, you have it in the bottom of the T tables. There are Z values down there in the bottom, 3 decimal Z values. On the top, you need to look at the probability in one tail, 5%, and you're going to find that 1.645. But I think you should remember that this is a number that we often use, right? Between negative 1.645 and positive 1.645, there's a confidence of 90%. So this is something we have introduced a long time ago. Okay, where is this guy? Test value. It's in the tail. Because it's in the tail, we will reject the null hypothesis. That means that we are affirming the alternative. Yes, morning students are better. The morning students in statistics class of Professor Flint are better students than the afternoon class. Not just this particular class, but every time he has those classes, the morning students will be better than the afternoon students in general. Again, it could be classes when it's going to be in reverse. We are at least 95% sure that the morning students are in general better than the afternoon students in the class of statistics. Maybe I should say course, right? The class would refer to the just one group of students, but in general, in the course of statistics, morning students will be in general better than the afternoon students. Okay, that's a conclusion. We have significant statistical evidence for that. All right. Okay, this is the story about the test of the two population means by using a z-test. What if you have a proportion? So I'm going to refer to this example with the last time. We were talking about you have 400 teenagers and 600, reverse, 600 teenagers and 400 adults, and they're watching some TV program. 1/2 of the teenagers like that program and 1/4 of adults like that program. So there was a kind of big difference between the two groups. There is a difference between the proportion in the sample. So I have two samples. The sample of teenagers, when I had a bigger value, 50% of them. Proportion in that sample, 50% of them, 300 out of 600 like that program. Okay? I'm referring to one example we did the estimate last time. And then I had the adults, and only 1/4 of them, 100 out of 400, like that particular program. So that was 25%. Okay? So could I conclude that based on that two sample, a fairly large sample of 600 teenagers and 400 adults, could I say that in general adults are going to, teenagers are going to look, like that program a lot more than adults? And last time we did the 95% estimate, I think, was that we come up with the, was that 95% estimate? I forgot already. Let me remember that. Remind myself. Yeah. We said that it's anywhere between 19 and 31% difference, which means that I'm 95% sure that it's at least 19% difference. 19% difference between the teenagers and adults in terms of likeliness of that program. Do they like that program? At least 90% of teenagers at least 90% is higher among teenagers than among adults. And maybe even as high as 31%. That's what we did last time. So I don't really need to test it. I already know the result, because that's what I concluded last time. But let's do the test, which will of course confirm the same. So I have the proportion of teenagers that like the program, 300 out of 600 is 50%, divide that, right? proportion of adults that like the program. That was 100 out of 400, so 1/4 if you divide it. The test setup is the proportion of teenagers in the population, so this is without hat, and proportion of adults in the population are that like that program are the same. Okay? The alternative hypothesis is, well, teenagers are much more in favor of that program than adults. So that's my alternative, right tail again. Okay? What's gonna change in my test value? Well, first of all, I'm gonna have again the z-value or the z-test, because the test of proportion is just like estimates of proportion must be, and it's going to be only z-test, and it has to have all large samples, and we do have large samples, 600 versus 400. This is gonna be the mean of the population in terms of polling. That's the mean of sample, excuse me. In terms of polling, that's the proportion of the sample. Proportion of the sample. Down there we have the variance of binomial random variable with one trial, Bernoulli random variable. We have that supposed to be this guy. And the same thing for the adult story. Okay? More, we assume that this and this is the same, which means that px and py is the same, and therefore qx, which is the complementary, so that px is 30%, then qx is 70%, right? So if these two guys are the same, then these two guys are the same. We always assume this is the same. So this and this is the same. Right? I don't know what that is because it's a population proportion. So I am going to use the average of these two guys to give the estimate for the population proportion. How do I calculate the average? You can't just make the average like add the 2 and divide by 2, because in first group you have 600 teenagers, in the second group you have 400 adults, so this is not proper average. The average ought to be, you know, how many things you have. That ought to play a role, right? So I have to be doing weighted average. So I'm going to have the average to be, this is calculated of 600 people. And this is calculated of 400 people. And then I have to make really the average, which is the both numbers. Okay. So this is weighted average. This is stuff you might have been doing in probability 103. I'm not entirely confident that you have done that, but that's how I'm going to get this. So in my story here, this is going to be, let's see, 600 times 0.5, which is 300, right? Plus 400 times 0.25 divided with 600 plus 400. You can write it, I know it's 1000, but you can write it like that. 600 plus 400. And this is an easy calculation, all the numbers are very simple. So 300 plus 100, which is 400. 400 divided with 1000 is 0.4. You check my calculation, make sure that's right. So the average is 0.4. You see, 0.4 is closer to 0.5 than to 0.25. Of course, because I have more teenagers in the sample, so it has to be weighted average. Okay, so I have 0.4. So that's going to replace this guy and this guy. They're supposedly the same. I am now using pooled. I pooled these two guys and made an average, a weighted average of these two guys as an estimate of the population proportion of both, because I'm assuming they're the same. So I'm going to have here PQ PQ. This is the same thing, so it's a common factor. And you know about a common factor, right? So you can extract the common factor and write it a little nicer, and use your formula. Okay? So I need to calculate this guy. I didn't put that in the lecture, so I'm gonna have to really do that now. It's not gonna be that difficult, but this is the formula for the test value. So I have over there 0.5, 0.25, downstairs 0.4, 0.6, 0.4, complementary 0.6, 40%, 60%. This is 1 over, what do I say is how many teenagers? 600. Plus adults 400. Okay? I'm gonna get an approximation, right? So let's see. We have a lengthy calculation here. I didn't calculate, so I have to do it now. 1 over 600, 1 over 400. I got some really small value. Then I have to multiply with 0.6. Then I have to multiply with 0.4. I get 1,000, and then I have to take a radical. I got some really small number. Okay. And then I have to turn it upside down. I need to find the reciprocal. I got that. I got 31 something, and this is 0.25. 0.5 minus 0.25 is 0.25. One way or the other, somehow you're gonna end up with this calculation, and I got approximately 7.906. I'm using 3 decimals. There's more digits to that, but I'm using that not to confuse the different stuff over there. So where do we have that? Test value deep in the tail here. I am not really making this up to scale. This is 1.6 and 7. This is almost 8. It goes like maybe here. So the only thing I need to know is it's in the tail, and it is in the tail, which means that I have rejection criterion. I just met the rejection criterion. Rejection criterion means this one is rejected, this one is accepted. Yes, the teenagers do like that program more. I'm at least 95% sure in that. Again, I already knew that, because last time we were doing estimate, we said that I am 95% sure there is at least 19% difference between the teenagers and adults in terms of how much they like that program, and it might be even up to 31%, right? So that I did last time, so I already know that teenagers do like that program more. But this hypothesis testing also confirms it. Okay? This is the hypothesis testing of difference of 2 proportions. Proportion of the teenagers and proportion of the adults that like that program. Not in this sample of 600, 400, but in general, among all teenagers and all of the adults. They have enough statistical evidence to conclude that teenagers will always like that program more than the adults. Okay? Okay, what if you are doing a t-test? what happens with the t-test, right? The t-test is the test for the difference of two means. Again, the difference of proportions is always based on the central limit theorem. It's always a z-test. The difference of two means could be a t-test. Why? The same thing as for the estimates. If you have unknown population standard deviation, then in that formula that we use, when you have to put a sigma, you would have something that you don't know. Okay? And that's a problem. Then you're doing approximation if you are replacing that with S. But for that approximation, you need to have large samples. You might not even have a large sample. So what else you need to have for t-test? You need to have a normal distribution of the population. Both of them, the X population and the Y population, if you're talking about the two populations. So if you do have that, then it's a t-test. So again, number one, you will have the normal distribution of X, normal distribution of Y, and number two, you will have unknown the population standard deviation. When does that happen? Well, if you don't know one, then they are unknown to you, right? You're talking about two people and you say, oh, these two people, I know this guy, but I don't know this guy. Well, then you don't know them. Oh, I know this guy, but I don't know that guy. Well, you still don't know them, right? When you don't know one, you don't know these two guys, right? So that's when you're using t-test. Unknown population standard deviation, normal distribution of X, normal distribution of Y. Okay, so let me give you an example. A researcher is comparing the weight of two groups of hens. One group of hens, there are 19 of them, they were fed with special diets. Another group of hens were fed with normal diet. What does that mean? Well, this first group was probably getting vitamins, steroids, antibiotics, and I don't know, whatever to give to them to make them heavier, because they're going to slaughter them and you're going to get that meat, more meat, and you're going to be able to get more money out of it. The other group of hen on a regular diet was probably eating corn or something, whatever the chicken eat. So whether there is a difference in the weight between these two groups of hens, what do you want? You want to find out whether this special diet in which you're spending extra money to give them something extra was actually making them heavier. So he was polling that, and he was collecting the data, and he found out that in the first group of hens the weight was 5.7 pounds, while the standard deviation in this group of hens was I'm reading the example, 0.6 pounds. That's a special diet. The hens are eating something extra. The regular diet, the hens that are eating regular stuff, they had we're gonna call them Y because they're smaller numbers, 5.3 pounds. And the standard deviation, they're not all the same weight, was 0.7 pounds. There are a little more standard deviation in the second group, so those regular chicken are a little more diverse in the weight. In the first group we have 19 hens, in the second group we have 24 of them. So notice immediately you don't have enough sample. I mean, the sample is small. Okay? You also don't know the population standard deviation. This is sample standard deviation, so you don't have any information population standard deviation. So now, if you can assume that the weight is distributed normally when they are eating diet, the special diet, and when they are eating regular diet food, which we're going to assume, then you can use a t-test. Again, you have a normal distribution of X, weight on a special diet, weight on a regular diet, Y, normal distribution, unknown population standard deviations. You don't know either one of them. Okay? So the setup for the test is, the weight is the same. The alternative hypothesis, I don't think so. I think the weight of the chicken or the hens on the special diet is more, heavier. They're heavier. The test value is the same as before. X bar minus Y bar. Down there, Z value would be this one. But this is not a Z test, right? This isn't a Z test. This is a T test. So what's the difference between the T test and the Z test? Well, we have the sample standard deviation here, rather than population standard deviation. So that's all there is the difference for now in the 1, 2, 3 things. Well, there's some difference here too. Okay, so you can calculate this test value. So you have there 5.7 minus 5.3 divided with 0.6. You have to square that. Divided with 19 hens in the first sample. In the second sample, 24 of them. The standard deviation in the second, 0.7. Work this out. I come up with the number that is 2.016. Okay? Rejection criterion. What are we going to use? I don't know. Let's say 5% again. If you don't have any better idea, that's a customary level of significance. I want to be at least 95% sure in my conclusion of rejection, if I have rejection. So I need to find this critical value here. This is not a bell curve. This is it looks like a bell curve. This is a T curve. T curve. Okay, now the question is only, T curves have degrees of freedom. What do we have here? 19 chickens in the first group, 18 degrees of freedom. 24 chickens in the second group, 23 degrees of freedom. What am I going to use? The one or the other or some combination of the both? As a matter of fact, in a serious statistic, we do use a combination of both. We do interpolate that. But I am not going to torture you with that. So we're going to use a conservative way. We're going to use the least freedom that is available, 18 degrees of freedom. The group that has a smaller degrees of freedom is the first group, 18. The second group has 23 degrees of freedom, so we're going to use 18 degrees of freedom. 18 degrees of freedom, the critical value with a 5% in the tail. And then, of course, you have to open the T tables. In the T tables, I am looking for the probability in one tail, right tail, 5%, 18 degrees of freedom. The number I'm getting is 1.734. That critical value here is 1.734. That's this number here. Oh, this arrow really doesn't look good here. Let me just erase it. That's your critical value. What's the test value? 2.6016 fits in the tail. Okay? It's bigger number than 1.734. Okay? We have our conclusion. Rejection criterion to be in the tail here, the test value is in the tail, means this is rejected. The rejection criteria is met, this is rejected, this is accepted. The chicken on the special diet are heavier. I'm not talking about this 19 versus this 24, I'm talking about general. If you feed the chicken, the hens, with this special diet, on average, they will be heavier than the one on a regular diet. So you might as well start doing that, if that's your goal. Okay, we have enough statistical evidence to that conclusion. I am trying to open the lecture, go back to an example. And I guess, yeah, I was using 5%. I was kind of a little bit worried maybe I'd use something else for the level significance. Okay. We do have one special case that I need to talk about it. So we were talking about the testing the difference of population means by using z-test, testing the difference of population proportion by using a z-test. By the way, that particular example I was finishing on in here is not in the lecture. It was just a direction with that. And I was also using a t-test. In that t-test, I was using conservative approach in selection of the degrees of freedom in my final curve. There was a t-curve, right? Which is the smaller number of degrees of freedom that you have in the two samples. So one sample is 18, another sample is 23 degrees of freedom, so I use 18 degrees of freedom in my final curve here. And the reason why you do that, if the population variations are not the same. I think that's the case here, because if you do the sample standard deviation square, you're going to have at 0.36, you can make a square of that. When you do the other sample square, standard deviation of the other sample square, you get 0.49. This number is this number here, 0.49. Doesn't look a big difference, but this number here is 35% bigger than this number here. Check it out. Divide them both, you will see that. So this number here is 35% bigger than this number. That's a difference. That is significant difference. Okay? The variation, the variances in the sample are different. Yeah, the standard deviation look close, but the variances are quite different. And that means that the population variations are not the same. What I would actually, I could even test it, but we're not going to talk about that. I think here that this chicken they're eating regular stuff, like corn or something, they have a bigger variation in weight. Well, these guys that are fed with those vitamins, hormones, and who knows what, steroids and whatnot, they got the antibiotics too. You get all of that in chicken. These guys are all, you know, fat, about equally less diversity in that. That's what I see here. So then, this approach we did was perfectly okay. But sometimes, it happens that the variation in the two populations are the same. Or at least that you can assume to be the same. So that's a special case. Okay? Let me give you an example when that happened. Again, we're talking about the t-test here. I have here an example that is in the lecture, that is number 6, example number 6. In this example, I have two groups of drivers. Two groups of drivers. Let's call them an X and Y group. The first group is a control group. The second group is experimental group. What does that mean? Well, I have an allergy drug. I am giving allergy drug to the second group. To the first group, I'm giving a sugar pill. They don't know what they are getting. Neither of them. In the first group, I'm doing the driver's test. It's a virtual test on a computer. The scores in the first group are 23, 15, 16, 25, 20, I got more of it, 17, 18, 14, 12, 19, 21, 22. In the second group, the group that gets a real drug, the allergy drug, I am also testing them on a driver's test, and this is 16, 21, 16, 11, 24, 21, data is in the lecture on the blackboard, so you can check it out. 18, 15, 19. (22, 13, 19). It happens to be that the both groups are equal number of drivers. I have 12 of them. So what do I want with this test? I want to find out whether this drug is drowsy or non-drowsy drug. Because if these guys in the second group, which got this drug, and not a placebo, not a fake pill, but the real drug, are they going to score worse? Because if they do significantly worse than the first group, then I should be concluding that this drug is, impairing the driving. So I can, I have to label that in a special label, in which going to say drowsy drug, or I don't know how they label them. Do not use this drug while you're driving. Right? If that doesn't happen, then I can just simply label it non-drowsy drug, so which means I can sell it to a little more people than without it. Okay, when you do this calculation here, you will end up. This is what my calculation shows up, and you can check it out. You do yourself. I end up with the mean of the first group to be 18.5 exactly, and I end up with the standard deviation in the first group to be 3.896. Now, okay, this is going to be approximation. It's not the exact number. And the second group, I got 17,916. With the bar on the 6, so this is exact number. So it goes 6666 and so on. And I got standard deviation to be 3848. One thing you notice immediately, this is kind of close. Standard deviations are close. But the question is not about standard deviation. The question is about variance. Variance. So I'm going to get the variance for the first group. You have to square the Sx, and I'm getting 15.182. And then I'm going to square the second group, standard deviation, and I'm going to get the variance, and that's 14,811. Okay? Now if you divide these two numbers, you'll see how different they are. 15.892. You can say the variance in the first group is 15, the variance in the second group is 15. It isn't really exactly 15. All right, to put the approximation here, wiggle. You know what? This number is 2.5% bigger than this number. It's almost nothing. 2.5%. The variance is 2.5% bigger. Now, in the previous example about a hand, I had that 35%. That's a heck of a lot difference. This I have 2.5%. Right? This number again is 2.5% bigger than this number. What does that mean? It means that I can conclude here that the population variation is not different. The variation in one population and variation in another population variances in one population and another population are about the same. That means that I can now approach differently here. I can make a more precise estimate. If this happens, that the variation in the population, the first and the second population are about the same, then I can do a more precise estimate. Okay? Now how is that going to work? First of all, what am I having here? Well, what am I testing here? I should really refer to that from the beginning. I'm testing whether the drug is drowsy or not. So assumption is the drug is not drowsy. That the test results with the drug and without the drug is going to be about the same. That's the null hypothesis. I get that without the drug is 18.5, with the drug is 17.9. There is some difference. So maybe without drug is bigger than with the drug. The driver's test scores without drugs are bigger than the driver's test scores with the drug. right tail, excuse me, right tail test. Again, this stuff here, this is just a straightforward calculation. It's not going to be much of a surprise here. But I'm not going to use Sx and Sy. What I'm going to use here is going to be a pooled value. Pooled value. Because I just assume that the population variances are the same. The variation in the population are the same. So which means that I will not use Sx and Sy separately, because I don't think that in the population is difference. I'm going to use the average of these two. Not exactly the average. I have to weight them again. That's called the pooled standard deviation. Pooled standard deviation. Or the pooled variance, if you're calculating variance. It's easy to calculate. I'm going to have to multiply the first one with the degrees of freedom, the first variance. I'm going to have to do the same thing with the second variance. Second variance, degrees of freedom, the variance, second sample degrees of freedom, right? Oh, the second one is y. And then I'm going to divide it with the all over degrees of freedom I have, which is the sum of two. This plus this, n1 plus n2 minus 1 minus 1. So n1 plus n2 minus 2. This is the formula for the pooled variance. Okay? Now I cook this nicely, so I have no problem of calculating that, but you do have to pull it in. This number here is 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Degrees of freedom 11. This number is 11. This number, square it here. I have it here, right there. This number is also 11, so 12 here again. Minus 1 is 11. This number here is right here. Okay? Downstairs you have 22. 12 plus 12 minus 2. In my case, so this is nicely cooked, I am getting the pooled variance to be exactly, or I shouldn't say exactly because it's always approximation, 15. Beautiful. Okay? So that's the pool variance. That pool variance will replace this guy and this guy here. More algebra for you. Common factor, which can be extracted. What do you do when you extract the common factor? You have to multiply both of them. The next step, radical. Factor, factor. Radical of one factor, radical of another factor. Radical of this guy, it's just a square. It's just going to be SP. So you can just pull it out. I don't have to have that much of it. Beautiful formula. Very simple, nice formula. This is the formula for the test value when you have the same variations in the two populations. That means the same variances in the population. The variances in the population are the same. You need to have a strong indication of that. Right here. In one sample, another sample is about 15. In both of them, the difference is 2.5% from one to another. I have indication of the same variation in the population. Or you might have another information that says that, you know, it's the same variation in the population. One way or the other, you need to have that, and then you have, instead of having two different standard variances of the first sample and second sample, you just have the pooled variance, which is your estimate for the population variance. How good at estimates is a different story, but that's what you're going to use. You're going to replace that in the formula whenever you have Sx and Sy, and the formula becomes simpler. You have this. Okay? So now you can calculate what's your test value. On the top you have the difference of these two numbers, so you're going to plug that in. You need to be doing that a little nicer than what I'm doing, right? It's gonna be approximation. Why? Because I'm gonna have this as approximation. Down there I have, oh, radical of 15. Radical of 15. This is a pooled variance. This is a pooled, standard pooled. Pooled standard deviation. I got that to be 3.873. And inside I have something really simple. 1 over 12 plus 1 over 12 peanuts. All right. Now, I am not going to. I'm too lazy to calculate that. I already have calculated that in the paper. I'm just going to tell you what that is. I'm going to separate this because there's lots of stuff written here. I don't have much of a board. This is the whole enchilada, 0.369. Okay. Once again, I'm going to use a T. This is a T test, T curve. Once again, I'm going to use 5%. If you don't like that, use something else. But I'm going to use 5% level of significance, which means this is going to be, again, 0.45. And I need now this number here. But this time, I have a pooled degrees of freedom. Pooled degrees of freedom is 22. In other words, degrees of freedom here, 11. Degrees of freedom here, 11, put together. Sum, total. 11 plus 11 is 22. So I'm looking for 22 degrees of freedom. T curve. 5% tail. Look at the T tables. 5% tail, 22 degrees of freedom. My number is 1.717. And now I'm looking for this guy being in the tail, rejection criterion. It isn't, it's right here. I'm not really precise, but somewhere closer to 0. This is much bigger number, 1.717, 5 times bigger, right? So, no rejection here. I cannot claim this. That doesn't mean I'm accepting this. I'm not saying this is I'm not saying this is true. I'm just saying that I have no statistical evidence here to claim that this drug is impairing drivers. So probably FDA will allow you to label it non-drowsy. Yeah, this old documentation will have to go. I don't think they will, because that's not enough. I think they probably want to have a much bigger sample of those drivers in the driver's test. But it looks like if I have some phony FDA, which will be happy with this kind of samples, then I could say, no, let's just label it non-drowsy. The drug, I have no indication, no statistical evidence that the drug would be impairing drivers, because my driver's test doesn't, even though there are some difference here, does not indicate statistically significant difference. But that as well could be because my samples are small. Right? That's a whole different story, so we're not going into that. Right? This is an example in which I was using pooling. Again, pooling, you're pooling variation of the sample. You are pulling standard deviation, only pulling variation, you're pulling standard deviation. You are also pulling degrees of freedom in your final curve in rejection criterion, 11 plus 11. If you don't have indication of variation in the population being the same, this is not variation in the population, it's in the sample 1, sample 2, but it's a sort of indication that it might be the same in the population. If you don't have that, then you're not going to be pooling. You're going to have that smaller degrees of freedom here, and you're going to have a slightly bigger formula, one more calculation there. Well, actually, there's a plenty of calculation here because of that, right? So you have a two situation, pooling, not pooling. Pooling is only done when the population variances are assumed to be the same. If you can assume that, then you have pooling. If not, then you have the old formula. So this is the new formula for the test value with pooling, where this guy is calculated out to here. You can take this square away if you put a radical on the other side, which you have in the lecture. You can see that. Okay? I know this lecture is harder than any other lecture we had so far. So here are a couple of the good things about it. And the whole story in lecture number 17 is always about independent samples. So this group of drivers and this group of drivers are different drivers. You could design this experiment differently. You could say, I'm going to give to this set of drivers, so 12 of them, I'm going to give them test with a placebo drug. They don't know what they eat. Placebo drug. Tomorrow I give them the real drug and I put them on the test again. That's really good idea, because now you're going to have the same people, so that the result and the test are not going to depend on whether the people are different, because they're the same people. But here you have another problem, because if they take the test the first time around, the second time around, they know something about the test, they must score better, right? So depending on your design, the test has flaws. But in the story we have, the whole 17 lecture is always independent. So this is not about the same set of drivers. No, this set of drivers and this set of drivers have no connection. They are independent. They're randomly selected independently. Okay? Now you can ask a question. What if I design experiment differently? So I have dependent set of drivers, like the same set of drivers. Then there's a different story. There's a lecture number 18 about it. Because of this semester going sideways, I decided not to teach this lecture. So I'm going to leave that. Maybe you want to read it. Lecture number 18 is there for reading. But I'm not going to ask you anything about it on the test. So I'm not going to bother you with that. But that will be the story. What do you do if your design of your experiment is that the samples are dependent? Because sometimes you want that. Okay? Less often, but sometimes you do want that. Right? That's not the story here. The whole lecture 17 is about independent samples. You have two populations, the samples are selected, they are not connected in any way. Right? So this is the story. We're talking about the estimates of the difference of two population mean, difference of two population proportion. We were doing a t estimate, z estimates. The proportion is always z estimate. We were now today talking about the hypothesis testing by using a z-test and t-test and the proportion z-test. We also talk about it, the pooled situation for the t-test, And that's pretty much all you're gonna have. Now there's a large homework associated with that. I would suggest you to do the homework as soon as possible because it will give you a lot more handle on it. There's lots of stuff here, many formulas, unfortunately. And the next time we meet, we're going to be talking about a TI calculator. How do you use TI calculator to do all of that with a TI calculator? TI calculator, of course, is going to give you p-values, right? P-values is the feature on the calculator. Now here we're just comparing the critical value and the test value by using the picture. Right? In the p-values, you're comparing the p-value and the alpha, the level of significance. If the p-value is smaller than level of significance, then you reject. That's a rejection criterion. That's the alternative to do that. So next time we meet, we're going to do that. Okay? I hope this is all okay with you. Lectures on the Blackboard. So everything is written in the lecture. All the example I talk about it. And I want you to read it if you want to read, or just watch this video again and do the homework. Do not forget that. Right? So I'm going to post a Zoom meeting, or next time we're going to do some calculator stuff about that. And I'm going to end the stream now.